These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. Today's discussion is about astigmatism, and we're going to introduce the second of the two very powerful tools that I mentioned earlier in this course. And this tool is the tool of power crosses. I said earlier, and I'll repeat it now, that there are in optics, as in much of physics, multiple ways to approach a particular problem. But if you have the opportunity to approach the problem employing either vergence or power crosses, you should, because they're such powerful tools. Okay, anyway, in order to begin our discussion about astigmatism, we have to understand what astigmatism is. In a purely spherical lens system in which there is no cylinder, rays of light converge to a point. And we typically draw this as two lines coming together and meeting as a point, and then splaying back out. But of course, this happens in 3D space, not on the 2D space of the page. So if you can picture a spherical lens converging system as producing a shape in 3D space akin to two ice cream cones attached with their two little points, then you can picture this sort of cone of light coming down to a single point and then splaying out to another cone of light. And that is what a spherical converging system looks like. The point is a stigma. And what we're going to describe now is a system that does not come down to a single point, that is an astigmatic shape. So we're going to now do the only multimedia portion of the optics lecture. And for it, I need you to use something that is of a different medium. What I'd like you to do is to get a piece of paper, and you can go ahead and put this lecture on pause while you do it, and then we will come back. Okay, I hope that you have your piece of paper with you. And what we're going to do is we're going to take a sheet of paper, I have mine here, and we're going to roll it into a little cylinder, which I have now done, and I hope that you have done too. And you're going to take your dominant hand and separate the index finger and the finger next to it. And you're going to, with the sides of these fingers, pinch the edge of your roll of paper so that you're compressing it into a little line between your fingers. You're then going to take your non-dominant hand and do the same thing on the other end of the tube of paper, except that you're going to make sure that these fingers are oriented perpendicularly to, or in truth, or orthogonally, but whatever, perpendicularly, to your first fingers, and you're going to pinch it off. And the shape that you're going to wind up with is a shape that describes the middle of the conoid of Sturm. And it is a shape that does not come down to a point anywhere, but has one focal line that is the paper as it is compressed to the shape of a line between the fingers of your dominant hand. And at the opposite end of the paper, a second focal line that is perpendicular to the first focal line, that's rotated 90 degrees from the first focal line. that is pinched between the digits of your non-dominant hand. And you can see that immediately next to your fingers, let's look at the line of paper that is pinched between the fingers of your dominant hand. And let's go a little distance towards your other hand from it. I don't know, maybe half an inch or a centimeter, something like that. If you were to make a cross-section through the piece of paper at that point, what would that cross-section look like? It would look like an oval with its long axis oriented in the same direction as the fingers of your dominant hand. Similarly, if we were to make a cross-section that were an inch towards the middle of the paper from your non-dominant hand, that cross-section would also be an oval with its long axis oriented opposite to the long axis of the oval that we cut just a second ago. If we were to slice this piece of paper right in the middle, right between our two hands, then the shape that we would get would be a circle. And that circle has a special name. It's called the circle of least confusion. So depending upon where we slice this conoid, we can get one of 5 shapes. We can get a focal line, which is the shape of this piece of paper right where your fingers are pinching it. We can get a focal line. Let's say that, for convenience sake, that this patient has a cylinder with an axis of 90 or an axis of 180. It doesn't really matter. We would get one focal line that's oriented vertically. We have one focal line that's oriented horizontally. We have the circle of least confusion in the middle. And between the circle and each focal line, there are ovals with their long axes oriented either vertically or horizontally. Now, of course, people can have cylinder and oblique axes where the long axis of the oval or the axis of the focal line can be something other than 90 or 180. But you sort of catch my drift. Okay, that's it for the multimedia portion of this lecture. Okay, let's talk about just some words here. With the rule means a patient with a cornea that is steep vertically. So those of you listening in the U.S., you can think of a football. A football is a torus. It is not a sphere. It has a long axis and a short axis. And with the rule would be the equivalent of a football in the passing position, where the long axis is horizontally and the short axis is vertically. Or in cornea terms, where the football is steep, is more curved vertically, and is less curved horizontally. The description of where the cornea is steep, the meridian of steepness, is given by keratometry. So if the Ks are steep at 90, plus or minus 20, we say that the patient's with the rule. If the Ks are flat at 180, it also means that they're steep at 90, and again, the patient is with the rule. Now, let's kind of work this through once, and we're only going to do this once because then I'm going to give you a shortcut that you will always use. In a cylinder, the power is oriented orthogonally, is oriented perpendicularly to the axis. Picture this. Picture having a can of soda standing up on a table. And I'm going to ask you what the axis of rotation of that 3D solid is, what the axis of rotation of that cylinder is. And the answer is, if it's standing up on a table, that the axis of rotation of that can is vertical. Now, if I were to take a cross-section of that can vertically, what is the shape that I would get? The shape that I would get would be a rectangle, a shape with no curves to it, a shape that has no refracting power. So along its axis, a cylinder has got no power. If I were to cut the can horizontally, I would get a circle. I would get the shape that has the most curvature of any cross-section that I could take through that can. The most curvature, the greatest power, the greatest refracting power of that cylinder is perpendicular to its axis. Let's take the case of a patient who is with the rule. And let's say that, for convenience sake, this is someone who is emmetropic horizontally, but has got too much plus power vertically. He's myopic vertically. Okay? So the Ks are steep at 90. Let's say they're 45 at 90, and they're 43 at 180. And again, the Ks tell you what the power of the cornea is at a meridian, and do not tell you directly what the axis is. They tell you what the power is. And it's important, by the way, that we use distinctly the two words at and axis, because they mean opposite things. So when I say at, I'm describing the power of a meridian. So we're talking about a cornea now that is steep at 90. What is the correcting lens that we're going to give for that patient? Let's say that we are using a minus cylinder, so in order to compensate for the cornea that's too much plus. We want the minus cylinder to have its effect vertically, because this is a patient who is too steep vertically. In order for the minus cylinder to have its effect vertically, its axis must be horizontal. You remember? Because the axis is perpendicular to the meridian of greatest refracting power. So we are correcting a cornea that is too steep vertically. We're going to use a cylinder that has its negative power oriented vertically. That means its axis must be horizontal. So the minus cylinder, correcting for with the rule, has to have its axis oriented at 180. Which is shown in the fourth plank on this slide here. The minus cylinder axis is 180 plus or minus 20. You can think of it this way, that the meridian of the cornea, the meridian that is flat, gives you the axis of the minus cylinder. And that's what we just said here. So we sort of worked it through. But going forward, this is the way that I want you to think about it. That the meridian that is flat on the cornea should correspond with the axis of the minus cylinder if we're correcting the patient with minus cylinders. If we're correcting the patient with plus cylinder, it's just as easy. The axis of the correcting plus cylinder is oriented in the same direction as the meridian of greatest steepness of the cornea. Where the cornea is steep, where the Ks are steep, that tells you the axis of the plus cylinder. Or where the Ks are flat, that tells you the axis of the minus cylinder. Anyway, with the rule, football in a position ready for passing. Against the rule means that the cornea is steep horizontally, is flat vertically, and it is the football in a position for punting, those listeners in the United States. So it's the opposite of with the rule. Again, this is plus or minus 20 degrees. Oblique, or oblique, means that the Ks or the cylinder are outside of that plus or minus 20 from 90 or 180. Okay, now we sort of get to the meat of this lecture. We're going to introduce an enormously powerful tool, and that tool is called cross diagrams, or more specifically, power crosses. if we were to take a -4 sphere and we were to examine the power of that sphere vertically and the power horizontally, and again, we're talking about power, we're not talking about axes here, the power of a -4 sphere vertically is -4. And the power of a -4 sphere horizontally is -4. Anywhere you slice it, it's -4 because it's a sphere. If we examine the power of a plus cylinder, and I am going to, in this optics course, deal primarily with plus cylinders because in my residency program, and to my knowledge in most ophthalmology residency programs in the US, we use minus cylinder. But I want you to be adept at using either minus or plus cylinder. So I'm going to force you in this course to primarily use plus cylinder so that you're comfortable going either way. This is a cylinder. Now, I would like you to think about this cylinder for 1 second before we go on about power crosses. This is a cylinder that has its power, its plus power, acting horizontally. If this is a can of soda, is this can sitting upright on your desk or is it lying on its side on your desk? Which one? This is a can that is standing up on your desk, so that if we were to cut this can horizontally, we would get its maximum power, which would be +5 in this case. And if we were to cut it vertically, we would get 0 power. So this is a plus cylinder axis 90, right? Because this is a diagram that describes the power of the cylinder, not its axis. So this is a cylinder axis 90. Its power is acting at 180. Okay, let's combine the two lenses about which we just spoke, the -4 sphere and the +5 cylinder. And we can do that with these power crosses by taking the diagram of the -4 sphere and the diagram of the +5 cylinder, and we can literally add them. Before we create any new cross diagrams from the two cross diagrams that I have here, let's literally read what the prescription is from the diagrams that we have on the screen. The sphere is -4. That's given by the cross diagram on the left. The cylinder is +5, and we know that it's axis 90 from our discussion a couple slides back. So we can look at this diagram and we can say -4 +5 axis 90. We're now going to add these two cross diagrams up. And we arrive at the cross diagram at the bottom of the screen here, which is, well, we take the two vertical portions of the power cross. One of them is -4 and one of them is 0. We add them both up and we arrive at -4. And we add the horizontal parts of the cross diagrams. The sphere contributes -4, the cylinder contributes +5. We add those up, we get +1. So our total power cross is what's shown at the bottom, where the 90-degree power is -4 and the 180-degree power is +1. Now this is just one more description of the same lens. We could have described it in the way that we did up top, which we did. That's what the -4 +5 axis 90 is. Now we have a total power cross. We can, if we want, look at this total power cross as if it were the sum of two cylinders and say, well, we could have arrived at this total power cross by employing a cylinder that is -4 axis 180 +1 axis 90. Now, no one writes prescriptions for spectacles like this as the union of two cylinders, but it would be an equally valid way of doing it. So this is one more description of the same lens. -4 axis 180 union with union with +1 axis 90. We can also take our total power cross and divide it up with a different sphere. Now, if we look at the total power cross, that's the one on the bottom that has one arm that's -4 and one arm that's +1, we can see that we started out saying that the sphere was -4 and that the difference between the two arms is the cylinder. So -4, the other arm's +1, the difference between the two is +5. So we know that the prescription can be described as -4 +5 axis. Well, we know that the +5 acted horizontally, so it must be axis 90. So -4 +5 axis 90. We could equally validly take the value of the other arm of the total power cross and use that as our sphere. So we started with a sphere of -4. Now we're going to take the other arm of the total power cross, the +1 arm, and we're going to say, let's use the +1 arm as our sphere. In this case, we say +1 is the sphere, and the difference between the two arms is what? Well, when we used -4 as the sphere, the difference between the two arms was +5. We had to add +5 to -4 in order to get the other arm of the total power cross, the +1. Now we're taking +1 as our reference point, +1 as our sphere. And in order to get to -4, we need to add -5 to it. So our prescription, our description of this lens is +1 -5. And where is the -5 acting? It's acting vertically, so it must have its axis horizontally. So we can describe this as +1 -5 axis 180. When you are transposing cylinder from minus to plus or vice versa, for the purpose of practicing optics problems, I want you to do it this way, with total power crosses, drawing out what the starting power cross is, adding it up, getting a total power cross using the other arm for the sphere, and working it through like this. But when you're in clinic and you need to convert something quickly, a patient comes in with a prescription that he's gotten from someone else that has got plus cylinder, and you need to convert it quickly to minus cylinder, you'll of course do the trick that we do in clinic, which is to say that the new sphere is equal to the old sphere plus the old cylinder. That the new cylinder is equal to the same value as the old cylinder, but with the opposite sign, and that we rotate the axis by 90 degrees. So let's try that with our initial prescription that we started out with, which was -4 plus 5 axis 90. So the new sphere is equal to the old sphere plus the old cylinder. So the old sphere was -4, and the old cylinder was +5. -4 and +5 is equal to +1. So the new sphere is +1. Let me point this out with the mouse. So we're taking the -4, which is the old sphere, and the +5, which is the new cylinder, which is the old cylinder. We're adding these two up to arrive at the new sphere, +1. We take the old cylinder and we say that's the same as the new cylinder, but with the opposite sign. So we're going from plus to minus, and we rotate the axis by 90 to get +1 minus 5 axis 180. Now, what are we doing when we do this pithy little trick? When we take the old sphere and add the old cylinder to it, we're just going from one arm of the total power cross to the other arm of the total power cross. That's what the definition of the contribution of the cylinder is. It's the difference between the two arms of the total power cross. So when we take the old sphere and add the old cylinder to it, we get the other arm of the total power cross. the sign of the cylinder has to change because we're moving the opposite way on the total power cross, not from the more minus sphere to the more plus arm of the total power cross, but from the opposite, from the more plus now to the more minus. So the sign of the cylinder has to change, and the axis rotates by 90 because that is the difference in angle between the two arms of the total power cross. So, of course, I want you to do this the faster way in clinic, but I want you to understand that while you are doing that maneuver, that little trick, that what in fact you are doing is transposing the two arms of the total power cross. The last thing that I want you to notice when you look at the total power cross that has -4 for its power vertically and +1 for its power horizontally is that those are the two options for sphere when you're writing this prescription. If you start with the one that is more minus, then you're going to need to employ plus cylinder to get to the other one. If you start with the one that's more plus, you're going to have to use minus cylinder to get to the other one. So if we start out with +1 for the sphere, we're going to need to use -5 for the cylinder. And if we start out with -4, we're going to have to use +5 for the cylinder. In the next lecture, we are going to apply the power cross to solve a problem that would otherwise be very difficult.